speaker will be Michele Trenti that will discuss, will show us some updates on the SPIRIT mission. So I leave the floor to Michele. Okay, yeah. I see the screen. Perfect.
Yeah,
okay.
Perfect. So thank you, Andrea. Thank you, Lara, and all the organizers of the first scientific workshop for the HERMES SP and TP missions. It's a real pleasure today to be here at the meeting remotely from Australia and present you with a brief overview of astrophysics with the Cubesats, focusing on the state of the field in general, and then zooming in on two projects that Australia is advancing in collaboration with colleagues in Italy. One, the SPIRIT mission, the Space Industry Responsive Intelligent Thermal Cubesat, which we'll see will be hosting one of the HERMES detectors and aim at improving the performance of detector compared to the baseline of the SP and TP design. And the second one is a concept under development for a rapid response near infrared space telescope called the SkyHopper, the Cubesat. So in this audience, I probably don't need to highlight the high cost and complexity of developing and launching a telescope in space. Yet, space telescopes have really a unique advantage over their ground siblings, as it is illustrated here in this image of the most iconic, I would argue, of all space telescopes so far, the Hubble Space Telescope, which is a $5 billion mission. Assets such as Hubble are above Earth's atmosphere, and therefore they can collect photons with both unparalleled efficiency and with reduced foreground noise. They can give us access to essentially all the electromagnetic spectrum, and in particular all the high energy spectrum, which cannot be essentially observed from the ground. Traditionally, access to space has been limited to complex projects, maybe not all of the size of Hubble, but still major endeavors, mostly limited to space agencies. However, technology is evolving very rapidly, and very much like the first computers were bigger than conference rooms, and yet less powerful than our phones. Nanosatellites' capabilities are growing really rapidly in recent years. So in principle, if we have tiny focused missions or constellations of nanosatellites, such as the HERMES Pathfinder constellations, we can leverage the technology development. We get advantage in terms of cost, the schedule, rapid development, and also because having smaller, more focused missions is not quite as expensive and committing time and resources as the flagships, it allows us to use more advanced technology by taking a little bit more risk and using solutions that may start from lower technology readiness level. So Cubesats were initially developed for educational applications, but the research use of Cubesats is now dating back more than a decade, and was in particular pioneered in 2008 and started then with the Colorado student space weather experiment, a 3-unit Cubesat launched in 2012, which led to 17 peer-reviewed papers. So quite an achievement for a few kilos of instrumentation in space and developed by students at the University of Colorado Boulder. So that's just one example of the growing number of research CubeSats that we have today, including HERMES. So the challenges that we are finding if we want to develop an astronomy CubeSat mission can be broadly characterized into three main groups. First, an astronomy CubeSat generally, but not always, and we have here the example of HERMES, needs excellent attitude determination and control in order to remain stable while it stares at targets. And this is particularly important if we are aiming at observations in optical or infrared. Generally, CubeSats had really poor ADCS, but the progress in miniaturization of star trackers, reaction wheels, magnetorcs has been enabling really order of magnitude progress in controlling the attitude of the satellites. Second, traditionally, CubeSats were limited to UHF communication of an amateur's band, and that essentially prevents any meaningful transfer of scientific data. However, the field is progressing rapidly, and now essentially S-band technology is being an established solution for communication with CubeSats, and even higher data rates communications are emerging, such as K-band and even optical communication. Finally, depending on the wavelength, thermal management is also a challenge in a shoebox size satellite, where there might be the requirement for an instrument to be cold, even cryogenically cold, for example, for infrared observations, and yet you need spacecraft avionics to remain warm very close to the scientific instrument. All these challenges are rapidly being addressed, and I think that the transformation and the groundbreaking result that has shown in full the capabilities of CubeSats for astronomy and astrophysics has been with the Asteria satellite. This is a 6U satellite being developed by MIT and JPL, which launched in 2017. It's an optical imager for exoplanet studies, and Asteria demonstrated sub-arcsecond pointing stability and high precision photometry. In the plot that I have here on the slide, we can see the RMS pointing stability in arcsecond on the vertical axis for space telescopes as a function of the mass of the satellite in kilos. And we can see all recent astrophysics facilities, and the characteristic performance line is shown in a dashed blue. The lower below the line for your class of mass, the better you are in terms of pointing stability. And we can see here how Asteria is substantially lower than other satellites in its class of mass, and it is actually performing about as well as satellites that are 10 times more massive. So this was really a great achievement, and reaching essentially a stability of the spacecraft comparable or even better than the point spread function. In addition to demonstrating this pointing stability, Asteria also showed the power of S-band communication with downlink data rates generally around 1 megabit per second. It is possible to downlink full frame images taken with a typical few megapixel detector on board one of these nanosatellites. For the future, we have Ka, Ku band communications, which are being developed and will allow an even greater downlink of scientific data from Cubesats. Asteria also achieved a super precise focal plane temperature control to the order of 10 millikelvin, which enabled accurate photometric measurement at the sub-percent level. Asteria was able to measure a 0.04% transit depth for 55 Cancri E transit. But still, Asteria was a passive design and was aimed at keeping the temperature stable, not necessarily actively cooling it. Beyond that, technologies being developed to reach cryogenic temperatures, either with passive or active cooling solutions. And I'm showing here in this image the CryoCube CubeSat. This is a 3-unit CubeSat designed to keep a small payload, the sphere pointed by the arrow, at around 100 Kelvin thanks to a deployable sun shield. This is a satellite which, based on the latest information I found, was deployed in January 2020, but no mission updates to the best of my knowledge, but hopefully we'll get some news soon on the outcome. Technology demonstration for active cooling with micro coolers is also ongoing, and I'll talk about this in a few minutes. Before that, let me show you a brief list of a few astrophysics missions that are next on the launch pad. The next year or so should see a couple of advanced 6U CubeSats for exoplanet studies, in particular focused on UV spectroscopy or imaging. CUTE is the Colorado Ultraviolet Transit Experiment. It's a 6U satellite for UV spectroscopy of transiting exoplanet atmospheres, essentially hot Jupiters or hot Neptunes. SPARCS is another 6U UV satellite. SPARCS stands for Star Planet Activity Research CubeSat, and it's a two-filter UV imager to characterize habitability around low mass stars by looking at the space weather that these stars produce. From 2022 and beyond, there are a number of high-energy either single CubeSats or constellations being developed for GRBs and gravitational wave electromagnetic counterparts. Burst Cube from NASA Goddard is a 6U satellite in this space. Of course, we have the Hermes constellation, 6 times 3U satellites, plus we'll see now Spirit also joining the constellation in a couple of years. And next we'll hear about Camelot. So all these should reinforce the idea that there is a lot of activity going on CubeSats. If you want to measure it quantitatively, if you try to look at how many abstracts in ADS include the word CubeSats, there has been a 10 times increase from 2011 to 2018. And in 2018, there have been over 200 ADS entries focused on CubeSats. So within this rapidly evolving landscape, myself and colleagues in the Australian community started asking a few years ago whether the technology was finally mature enough to support the development of a concept for an innovative nanosatellite focused on near-infrared imaging, and discovered that yes, we think we can do it. We can be effective, even though we are a little fly compared to larger siblings such as Hubble. So the idea that we have been developing is of an infrared shoebox space telescope hosted within a 12U, 22 kilo, 50 watt satellite. The primary instrument that we designed is a 15 centimeter imager with 4 bands covering 0.8 to 1.7 micron plus 2 narrowband filters on a portion of the detector. The 1.5 square degrees field of view is covered with a 2K by 2K array, and the telescope is hosted by a highly stable spacecraft with a 1-axis jitter of 3 arcsecond RMS 1 sigma. A key feature of SkyHopper is a rapid slewing capabilities, 2 degrees per second, and 24/7 low latency latency between ground and the satellite bidirectional for a 2-year primary mission. So what motivates these specifications and design that we converged upon? SkyHopper's science cases are focused on making contributions to key active areas of current astronomical research that fit uniquely the idea of having low noise IR observations, which are possible only from space. In particular, we are aiming at contributing to 2 themes: the discovery of Earth-like planets orbiting around low-mass stars, which are the most abundant in our solar neighborhood. So in the SkyHopper, we might be able to detect some of the closest potentially habitable worlds, then enabling further follow-ups with flagship class facilities such as the James Webb Space Telescope. The other main science goal for SkyHopper, and actually the one that led to the birth of the concept, is to contribute to the cosmic origin problem, characterizing the properties of the first stars and galaxies in the universe, in particular through gamma ray burst observations. And so here you can start seeing the complementarity and the connection with the HERMES project. The key science case of SkyHopper is the rapid response to transients, in particular to the long duration GRBs that we would like to identify in the epoch of reionization. So our goal is to measure the photometric redshift from the afterglow and identify sources at redshift greater than 5, that is in the first billion years, to then trigger immediate spectroscopic follow-up. So the idea is that SkyHopper will carry out, for example, some exoplanet observations. There is a GRB triggered by Swift, Swarm, or HERMES. We can then rapidly repoint SkyHopper and observe the afterglow in the near infrared. Because SkyHopper is very nimble, we named the project after this capability, And our logo features the Spinifex hopping mouse, which is Australia's smallest marsupial living in the central desert. And with these capabilities, our science mission simulation tell us that we have a good chance of doubling the sample of currently known GRBs at redshift greater than 5, which is just over a dozen sources within about 2 to 3 years of operations. In order to do so, the key requirement that we need to achieve is the rapid photometric redshift determination at redshift greater than 5. So we need a high point source sensitivity to observe the majority of the afterglows, 19.5 AB magnitude in 600 seconds of observations. We want to simultaneously observe in 4 bands from 0.8 to 1.7 micron and be on target within a few minutes from the trigger if the source is visible from our orbital position. So the key challenges are an actively cooled IR detector for reducing dark current and near real-time uplink and downlink of targets and photometry. So our ambition with SkyHopper is to be the first infrared imager actively cooled to 140 Kelvin on a CubeSat. And here is a concept of our optical design. SkyHopper is technologically quite challenging. So what can we do in terms of risk mitigation? And here, addressing risk mitigation for SkyHopper in collaboration with our Italian partners at INAF led us to take advantage of the first call for proposal ever issued by the Australian Space Agency, which is an agency just over 2 years old. And so we submitted a mission concept for a bilateral project for a 6U 10-kilo CubeSat with an Australian-made spacecraft and an Italian X-ray instrument, the HERMES instrument. This was the only project selected for flight by the Australian Space Agency. So we're very proud to have an Italian-Australian collaboration for this first mission by the Australian Space Agency. And our key goals are to showcase the maturity of the Australian space industry, which is growing rapidly in recent years. Scientifically, we aim at augmenting the HERMES SP and TP capabilities. And the link to SkyHopper is to mitigate risk of that more complex CubeSat by flying the thermal management subsystem and the real-time communication subsystem. At a glance, we can see here in this slide the SPIRIT spacecraft concept. The primary payload on SPIRIT is the HERMES payload, which will be actively cooled by the TheMIS payload that we are developing at the University of Melbourne. The CubeSat will have low latency communications to the ground thanks to the Mercury payload. And the satellite will also host an experimental technology demonstration electric propulsion payload with the bus developed in Australia by Innovor Technologies. SPIRIT is quite complementary to HERMES on multiple dimensions. In particular, we designed SPIRIT to be flown on a sun-synchronous orbit, offering a near orthogonal plane to the equatorial plane of the Hermes constellation. Second, SPIRIT cooling will improve Hermes performance by cooling to about -25 to -30 Celsius the GAGG crystals. And lastly, because of Australia's geographic location, we have opportunities for ground segment cooperation. Let me just very briefly show you the thermal management concept for cooling HERMES. It's based on an efficient Stirling cycle microcooler to keep the payload within its operating range down to -30 Celsius and half Kelvin stability. And in particular, we aim at testing deployable radiators and explore active vibration cancellation if we have resources. The rapid communications will be achieved by the Mercury subsystem, which will combine Iridium duplex and Global Star simplex user terminals to maximize the chances of timely communication, and we'll have artificial intelligence capabilities on board for switching between the two systems. The timeline of SPIRIT is very compressed by the nature of the call of the Australian Space Agency. We need to be on delivery to the launch service provider in less than 2 years. So our plan is currently ongoing. We just finished the preliminary design review this afternoon here in Australia. The plan is to get HERMES down in Melbourne in about 1 year or 11 months. Just before I finish, let me comment briefly on the future. I think that the nanosats really have a growing role in astrophysics. They complement rather than compete with flagship projects. And one area where I'm very excited in terms of opportunities, I think, is the distributed aperture space observatories, where constellation of CubeSats can work with each other. Particular interferometry would be a major achievement, or if we want to be more speculative, maybe assembly in orbit of segmented mirrors from multiple satellites. So very happy to leave up the summary and take any questions.
Okay, Michele, thanks a lot for a very nice presentation.